ask about that one. This is back on the second page, and I know the numbers are all over the place, but it's number 2, the one that has the rod with a sphere at each end, and this one is 3m, and this one over here is simply 1m. That's the mass. And there's a pivot point over here where that's L and that's 2L. And so the question is, what is angular acceleration, alpha? And I told you, I think, the answer is A. And some of you got A. Did some of you get A for that? I think. G over 7L. Let's go over it and make sure you understand how we got that. You're going to get it by our second law of it's the sum of all the torques equals I alpha. And you're going to solve that for alpha. Okay, so let's do that. Here's the pivot point. So let's add up all the torques. That's the first thing, add up the torques. Well, this torque is 3 MOG. Don't forget it's a force, so technically it's mg. And its distance from the force to the pivot point is L. Okay, so that's a torque. That's the torque from this force. That one's tending to make it rotate counterclockwise, so we'll make that positive. This is the other torque over here, and it's tending to make it rotate clockwise, so we'll make it negative. Its mass is MO, so the weight is MOG. And its R is 2L. Okay, so that's the sum of the torques. And that's got to equal I alpha. Well, let's go ahead and add that up. What do you get when you add that together?
MOGL.
I need to move that because Lily's just looking at your hair, Lucy. Which is fine.
I can sit here and we can put it there.
Whatever you all want to do. But that's okay right there, probably.
That's good. That's what we've been doing.
Just don't knock that off onto the floor and break it into pieces.
Hey,
It belongs to the school and they'll sue me for breaking their surface.
And how dare you?
It would cost me more than
I will watch it with you.
Oh my gosh, that was a sad statement.
I'm going to edit that part out.
You don't have to.
That's going to be on YouTube that I complain about. I'm not complaining about how much I get paid. I'm happy. What do you get when you add this and this? What do you get?
MOGL.
MOGL. Right? It's 3 minus 2. There you go. It's 3 minus 2. 1 MOGL. All right, that's the sum of the torques. Now over here you've got I, so here's the real reason I'm doing this. We haven't done this very often. If there are two different masses, one here and one here, 2 different torques, each one has an I, and they're not the same. So you need to add up the I's for this. This is really the sum of all the I's as well. You can put that there. So, but I is scalar. It doesn't have a positive and negative like the torques do. You just add that I plus that I. All right, so that's what I wanted to point out. This I would be mr squared, and the m is mo, but the m, I'm sorry, is 3m. So it's 3mo L squared. Okay, that's the mr squared. That's the m, and that's the r squared. Okay. This one is is mr squared, and its m is simply mo. Its r is 2l, and remember it's r squared. So you've got to do it like that. That's the r, but it's r squared, so it's 2l squared. Now you're just going to add those because it's scalar. You don't have one positive, the other negative. You just add the i's. What do you get when you add this plus this?
7MOL.
You get 7. Where did the 7 come from? That's 2 squared. Don't forget to square you don't just square the L, but you square the 2L. So that's 4L squared. That's the same as MO 4L squared. So that's 4ML squared. That's 3ML squared. They add up to 7 MOL squared. That's the I. And then that's the I. And then you solve that for alpha. That's what you had to do in number 2 here. So it's going to be this equals 7 MOL squared alpha. So you divide this by this, and when you do that, it simplifies down to G over 7L. We okay now? That's how you do number 2. And we kind of ran through that fast yesterday, but I wanted to make sure all of you understand where we got the I. Where'd the 7 come from? In the answer, even though it's 7, that's where it came from. Okay, any questions about that? This equation then that you've learned for the second law of motion, the angular version, is the sum of the torques. If there's more than one, you have to add them up, and that's vector, positive, negative. But it's also the sum of the i's, add those up, and that's scalar. You just add the mr squared plus the mr squared. All right, moving on. How far did we get yesterday? What is the next one we should be on? Anybody know? Did we get to number...
That was the last one we did.
That's the last one we did? Okay, well, there you go. Let's move on then to number 11. And here you have a wheel with inertia I, and its angular speed omega, and it's increased from 0 to omega f. There you go. So it goes from 0 to omega f for final, and it's in time t, capital T. So 11 is what is the average net torque on the wheel. What did you get for number 11? We're going to call Ohm Minho. T. How many think it's D as in dog? You're all correct. All right, any questions about that? That's torque equals I alpha, and plug all the numbers you have in there and solve it for torque. Okay. Number 12 on the next page still is referring back to the same wheel, and it says what is the average power input during the time interval? Power. All right, what do you have for power? Claire.
B.
Did you say B? Boy? How many put boy? Not very many boys, but B is right. So some of you did. Power, you can do this 2 ways. Power is work divided by time. And I don't know if you do it 2 ways or not, but because of conservation of energy, the work for a wheel, the work to get the wheel rotating is equal to its rotational kinetic energy once it's moving. And it went from 0 to something, so it's equal to its rotational kinetic energy that you got it up to. You had to do that much work to get it up to whatever that is. Well, that is 1/2 I omega squared over T. And just because of this equation. So if you plug everything you know in there, well, that is what you get. And that's what answer B is. If you look at B, it's I omega squared over 2T. That's either 1/2. You could put that as 1 over 2. I omega squared. There it is. T. Okay, so that was the yeah. You don't need the 1. That's the answer. Everybody see how you came up with that? It's conservation of energy that work and K are equivalent. That's it. Okay, look at number 10. This time we have this solid cylinder of mass M and radius R, and it has a string wound around it. It's a solid cylinder. So you already know that I is 1/2 mr squared, but they tell you that down in the question, in case you didn't know. All right, a person holding the string pulls it vertically up. The cylinder is suspended in midair for a brief time. It's not, the whole cylinder is rotating, but it's not moving up or down. It's just suspended in air. The tension in the string is T, and the rotational inertia on the cylinder about its axis is 1/2 mr squared, and 10 is what's the net force. Let's draw the free body diagram on it. You have here tension, and they actually called that T. So did they call it T? They did. The tension in the string they're going to call T. So we'll label it T, because they did. What's the other force acting on this thing?
Gravity.
It's just the force of gravity, which comes from the center of mass, the center of gravity, it was called. And so you draw the mg right there. That's just the weight of the cylinder. Okay. Now, is the cylinder moving up or down? No, it's suspended in midair. So what must be true about T and mg? They have to be equal. See, the sum, this is not torque, this is the sum of the y forces must be 0 because the whole cylinder is not moving up or down. So that's true, therefore T is equal to mg. Now you just know that even without reading the question. You look at your diagram you've drawn and you figure that out. Oh, T is mg. Well, now let's read the question. The question is, what's the net force on the cylinder during the time interval delta t? What's the net force on it? Well, it's 0. The answer is D. Did you all put D? Okay, very good. The up has to equal the down because it's not moving up and it's not moving down. It's in equilibrium in the y direction. So that, unless you got tricked into thinking that was a hard question, that should have been easy. Number 11, the linear acceleration of the person's hand. Now this one's not as easy. Let's see if anybody got this right. I bet somebody did. Number 11. What'd you get? Tony.
I got B.
B, 2G. Anybody else get B? Erica, you got 2G? Anybody else? Because 2G is right.
No.
B is correct. Did you get that, Erica?
Yes.
Look at that. Look at you. Hey, YouTubers. Erica just got the right answer. I'm just saying, now the entire universe, because it's going to be on YouTube where it's public. I can't give last names because of that or show your face. But I have this girl in my class. Her name's Erica.
It's me.
I also have a boy in my class named Tony. They got it right. Okay. All right. I don't really mean to erase it. Let's figure out how. All right. Figure out how. The question is the linear acceleration of the hand. Linear acceleration, not alpha. It's A, linear acceleration. But A is the same as translational acceleration from this force. So T is the force. So you've got F equals ma, but that force is causing rotation, isn't it? Here, you can't really do this to get, and that is what they're asking, but you can't, and the force is T, so you can say T is equal to ma translational, but the mass in that equation would be the mass of the hand. Who knows what that is? See, it's the mass of the thing accelerating in a linear direction. Well, that's the hand. We don't know the mass of the hand, so it kind of throws out. We can't do it that way. Okay. What we still know though is this is a force. This is creating a torque that's causing rotation. Okay. So the way we're going to do it is the sum of the torques is equal to I alpha, and then the translational acceleration is R alpha. Is that really true? That's true, right? Yeah. So we're going to find alpha this way and then plug it in here to get the answer. That's where we're going. All right. So the sum of the torques, there's only one torque, and that's T. That's this force. They labeled T. This one's not creating torque because it's at the rotation point. Okay, so that's no torque. This is the only torque, and it's equal to I, which is mr, which is 1/2 mr squared times alpha, and we're trying to get alpha. So alpha would be, if I just solve that for alpha right now, it would be T over, is that really true? T over 2 mr squared? No.
2T?
It would be, yeah. So 2, is that true? Yeah. 2T divided by mr. What happened to the, I'm sorry. Where's my mistake? I made a mistake. What is it?
You forgot the R.
I forgot the R. Very good. This is torque. That's just a force. torque is FR, and so that's TR there, and so that's going to cancel one of those R's, and so that makes it be this. Alpha then becomes, now I'm circling it to point it out, but that's not the final answer. That's alpha. 2T over MR. And they called R capital R, so let's use the same letters they do in the question. Now if I plug that in here, I get R times alpha, and alpha is 2T over MR, and so that's going to give me the right answer. The R's cancel. I get 2T over M. No, I don't. I get, what did I do wrong now? Oh, oh, I left out G. I left out something again. Really? Oh, I know what I did. There's no T. If you look at the choices, there's no T in any of the choices, is there? I need to put something in for T. We already said T was equal to mg. So instead of T, write mg. There you go. Now the m's are going to cancel.
Why do you know to do that?
And the R's cancel. Well, when you look at the choices, there's nothing with a T in it.
But there is something.
Oh, there are some T's.
Yeah.
I take it back. Well, if they had left an answer that said 2T over what used to be there, M, that would have been the right answer, but that's not there, is it? They have T over M, but they don't have 2T over M. So that really would have been a right answer, but it wasn't there. To get the correct answer, then you had to recognize T is the same as mg, and when you do that, the m's go away. We already canceled the R's, and you get 2g. You just get 2g. The m's cancel. Yeah, that's it. Now that was kind of complicated, and if you missed that one, that was one of the ones that most people missed when it was on the AP exam, because you had to do a lot of work. Some multiple choice questions you'll look at and the answer comes, but some of them you're going to have to spend some time with it if you're not just going to guess. And so you need to be prepared for that. Okay. Any questions? See, even I didn't know it. I was up here doing things, but I forgot the R. It's easy to make little mistakes. Even when I put in the R, I came up with an answer that wasn't one of the choices because I'd left a T in it. And that will happen to you too. You'll say, I got an answer, but it's not one of the choices. So keep going. You had to change the T to mg. All right, that's that. Let's move on to number 1 below that. It's another one that's going to be a little bit of work. What is your answer? The bowling ball, the question is the maximum vertical height to which it can roll as it ascends an incline. Okay. What'd you get? What'd you get, Lucy?
D.
D is in dog? How many got D? D is correct. This is conservation of energy. We may not take the time to work the whole thing, but it's this again. U at the top, when it rolls up, it has U, which is mgh, and that's what you're solving it for. Okay, that's the question, what height? And this is, one of these is 1/2 mv squared, and the other one is 1/2 I omega squared. And to go back to where we did that, we worked the problem in class. It took us 3 days, but we were doing this. And in the end, we found that what makes a difference is the fraction in front of the I. Because the m's are going to all cancel out, the r's are going to all cancel out. They don't matter. The mass of the bowling ball doesn't matter. Okay, so go back and look at that, and rather than me take the class time to spend a lot of it here. But you will get answer D. Okay, did you have a question, Erica?
No.
Okay, let's move on to the next page. This one has this contraption you see in the picture. And those rods are both kind of nailed to the axis in the middle. so that as it rotates, at the very top, they've got this little swirly thing they're calling omega. So as the axis rotates, so do these things here. And so they have the same omega. That's M, and this one is 2M and 2M, and this is 2L, and that's L. Okay, and so this whole system is rotating at this with the same rotational speed, same angular speed, even though they have different lengths and different everything. All right, so the question is, what's the ratio of the angular momentum now, L, of the two upper spheres to the two lower spheres? So let's see if you got it right. Who has an answer to this? Jaden, what do you have for number 3? Which one? What? Do you not have that on your paper? Oh, did you skip it?
I thought these two, that this was like a good page.
Okay. Cole, what do you have for number 3?
D.
D is in dog? Anybody else get D? Some of you did. D is correct. D is correct. This is asking for the ratio of L to L, or this is the, I think it was the upper ones to the lower ones. Okay, so that's what you have to think about. And L is I omega. And so it's the I omega for these over the I omega for those. And there are 2 of them. And so it's and we may not take all the time, but it's ml squared plus ml squared on top. That's this momentum plus this momentum, and they're in the same direction. They're all moving in the same rotational direction. Okay, so just add them over the momentum for these 2, and for those 2 it's 2m times 2l squared plus 2m times 2l squared. Okay, so if you simplify, that's it. That's the momentum of the top over the momentum of the bottom. So just simplify that whole thing and it'll come out 1/8. All the m's and l's cancel out, of course. Okay? All right, let's move to the person walking on the board supported by an egg. Let's see if you got it right first. The question is, how far from the end of the plank with the brick can you stand and not break the egg? So it's the distance from the person to the brick. That's the question. The maximum distance from the person to the brick. If you go any farther, any closer to the egg, it'll break. See? Okay. What did you get for that? Erica.
I think I got it way wrong because I read the problem wrong.
Maybe you got it right. Give us your answer.
I got 0.4.
Anybody else get 0.4? I'm sorry, 0.4 is not right. Did you get 0.4?
I got 1/3.
1/3 of the board?
Like a meter.
Well, 1/3 of a meter. 0.3 or so. Okay, it's more than that. The whole board's 8 meters long.
Yeah.
Right? Okay, here's how you do it. By the way, somebody got it right, I'll bet. Anybody get a bigger number than that? What'd you get, Lucy?
I want to say if you're wrong, but I got 2.7.
Anybody get 2.7?
Oh, come on.
I have a 2.1, I think. Did you get 2.1? So it's close to 2.7. Let's look at it.
Hey.
Here's the egg pushing up on that end of the board, and you're told it can only push with 150 newtons. So if that becomes any more than 150, it's going to break. So that has to stay at 150. Then over here, the brick's pushing up as well. We don't know how much. And here's the weight of the board, which shouldn't be that long. I kind of got too excited about that. It's 60. And then there's the weight of the person. which is much longer, is 450. Yeah. So here's the free body diagram. Do that first. Then you're going to set the sum of the torques equals 0, because you don't want it to rotate. Where would we choose a pivot point?
The brick.
Pick the pivot point to be at the place where that force will go out. It won't be in the equation, and we don't know what that is, so that's a good thing to let that out. Let that go away. So that will not be in the equation, but the rest of these will. So you've got to add up all the torques. And so the 450 is times R, because that's what we don't know. How far is the person's weight from the brick? So that's our unknown. By the way, if we're putting the pivot point here, that's tending to make it rotate counterclockwise, which is positive. That one then would also be positive, so plus 60, and it is a distance of 4, because it's right in the middle.
That's what I forgot.
It's right in the middle, 4 meters away. And then negative would be this one, clockwise. Its force is 150, and its distance is 8 meters from that end to the other end. And that all has to add up to 0, so that's what you do. If you do that, you'll get the right answer, which is
2.113.
Well, we can't see the equation. There you go. Plus, she wanted a chance to see Lucy again. All right, so that should come out to be 2.1 meters from the brick. And that's what the question was. How far from the end of the plank where the brick is can you stand? All right, everybody see what to do on that?
Yeah.
Okay. Then let's look at a few of the focus questions. So open your book and get your answers to those out. Your book should be open to the end of chapter 9 so you can see the questions. And they are on page 200 something. I'm getting closer. 276. 276. Number 1. The wheels on a moving bicycle have both translational, think of that as linear, and rotational motions. What is meant by the phrase a rigid body such as a bicycle wheel is in equilibrium? If the bicycle wheel is in equilibrium, what does that mean? Steve, what did you put for number 1? Do you have an answer to number 1, Steve? Why not? It was homework due yesterday. It was due yesterday, Tony. So everybody should have it today, shouldn't it? Should Steve have it today? Yes, he should. Kyle, what did you put for number 1?
A.
How many put A? The body cannot have translational or rotational motion of any kind. That is not A. It could be in equilibrium. What, Sarah, did you put?
D.
How many put D? D is correct. The body can have translational and rotational motions as long as it's not accelerating. Remember, if you're moving at a constant speed, your acceleration is 0. So yeah, if the wheel's moving at a constant speed, if it's rotating at a constant speed, all those things are 0 acceleration, and that's equilibrium. So it can be moving. Just can't be speeding up or slowing down. Number 3, there's the drawing, the overview of the door, and there are some forces there. Rank the torque that each force produces, largest to smallest. All right, then Claire, how did you rank, or which one did you pick?
I put B.
B is in boy. Who else put B? Just about everyone, so B is correct. 3, 2, and then 1 and 4 are the same. Let's look at 1 and 4. Why are 1 and 4 last, and why are they the same? What are they? They're both 0. You need to look at the drawing and make sure you understand why they're 0. 1 is 0 because it's at the pivot point, so R is 0. The other 0 because it's parallel with R. Okay. Number 6. you got 5 hockey pucks, and the drawing shows the forces that act on them, and some are F, and some are 2F, and some are 3F. So the question is, only one of those pucks can be in equilibrium. Which one is it? So, do you know, Steve, which one it is? Did you say B as in boy? B is puck number 2. Puck number 2 is not in equilibrium. Nope, not number 2. Number 2 would be rotating. If you look at the F's, they're both counterclockwise, and so it would be rotating, so that's not equilibrium.
Oh, D.
Did you say D is in dog? Is that what you meant to say last time? Correct. How many of you put number 4 was the right answer? That's true. Number 4, the torques cancel each other out, and then the forces to the right are equal to the forces to the left. Everybody see that? Okay, moving on. Number 8. You see the picture there. There's a box with 3 forces acting on it. The question is, which statement is correct? Okay, so which one did you pick for this, Sarah?
A.
A. The box has translational acceleration, but not angular. Anybody else put A? I'm afraid it's not A for the 2 of you who put that. So, Minho, what do you have for number 8?
T.
C,
D.
Cat. D, dog.
D.
How many put dog? Yeah, several people put dog, but it's not D either. I'm sorry. Who has a different answer? Erica?
I put C.
Cat?
Yeah.
Anybody else put C? Cole did, and Claire did, and Lucy's fixing her
I
hair.
didn't. I'm sorry.
It is C. You're correct. The box will have an angular acceleration, but not a translational acceleration. Let's look at that because not many of you got that right. Let's look at it. Here's the box. It's a square-looking box. There is a force F1 this way that looks like it's 2 units. If you look at the graph paper, that's F1. And there's a force right in the middle here that's 2 units down. That's F2. And the units I point out because the length of the vector is how strong it is, right? And then there's a force over here that's F3 that's at an angle. And if you look at the graph paper, it was 2 units to the right and it was 2 units up. That was 2 and that was 2. All right, so X forces, 2 to the right, 2 to the left, they cancel out. Y forces, there's 2 up and there's 2 down, they cancel out. So in the X and Y directions, it's in equilibrium. It's not going to accelerate horizontally or vertically. All right, so that was the part that said it will not have translational acceleration. That means left or right or up or down. But the other part was angular acceleration. Would the if you put a pivot point there, would it be rotating? And it would be because this is producing 0 torque. But it's lined up with the pivot point, so that's not involved in torque. This one would be tending to make it rotate clockwise, and it's F, it's the 2F times that R. This one is longer, and it's tending to make it rotate counterclockwise. And this, if you look at not the components, but the F3, it's longer than this, but it's got the same R, so this is creating greater torque. That's more torque than this one. It's going to rotate that way. So it's not in, they don't cancel each other out. It will rotate, therefore it does have an angular acceleration. Okay? All right, moving on to number 10. Number 10, you have that picture up there at the top of the page with the 3 spheres. and they're rotating around that line on the left. That line on the left is the axis of rotation. So I hope you got the picture. Like that entire ball, that 10M ball is, there it is. Here's the rotation. That whole ball is rotating around like this, around this axis point. And they're all doing that. All right, the question is rank the three objects according to their moments of inertia. How did you do that? Lucy, what do you have for number 10?
I have D.
D, dog.
D.
C, cat. D, dog.
D dog.
How many put D, dog?
Oh, great.
Erica, fix your hair. But I don't think that counts. You have to actually raise your hand. All right, I'm afraid it's not D. What did you put? Nate.
A.
How many put A for number 10? A, apple. 3 of you. It's not A either. There was a different answer. Do you have a different answer, Tony?
I put B.
How many put B, boy? B is correct. B says ACB. Here's what you do. The question is about their moment of inertia, right? Which would be mr squared. It's a sphere, but all of the mass is out here on the end of the, you know, this is R. There's no mass between here and there. So think of it as mr squared. I is equal to mr squared, and then you see, just add them up. For the first one, it's 10m times r, which is 10 mr squared. The r squared would be 1 squared, which is 1. Okay, so that's 10. I'm just going to write the numbers for comparison. The next one down was 2m times 2r squared, and that would be 2 times 4 is 8. Now remember the r squared, the r has to be squared. Okay, so that's 2 times 4. And then the next one was just 1m, but it was 3r squared, and so that's 9 times 1, which would be 9. So for that last one, it would be 9. So see, that's the most, that's next, and that's last. The thing you're doing is multiplying m times r squared. But you've got to remember to square the r, or else you get it all wrong. Okay, moving on. Number 12. You got that seesaw looking thing down there. And it's got blocks on each end, and it tells you the distances to the pivot point. All that's in the problem. And the question is, determine the magnitude of the angular acceleration. Okay, that would be this. Torque equal, and the sum of the torques, add them all up, is equal to I. It's the sum of the i's again, times alpha. Okay. All right, so let's see if you got this right. Who has an answer? I think Jaden has an answer. Maybe he wants to give us on number 12. So what? 0.13. Anybody else get 0.13? Because I have 1.3. Anybody get 1.3? Maybe mine's wrong. Did you get 1.3, Minho? Okay. Let's look at it. The sum of the torques is 16. What? I have 16 when I added them up. All right. No, but yes, it's 71 minus 55. Let me draw that up here. For the sum of the torques, here's this big thing, and here's a little thing, and here's the pivot point. So for this one here, it was mg times r. Remember, it's the force times r. And the r was 0.6, and the mg was 12 times 9.8. All that adds up to 71. Mg times r. Over here, it was only 4 kilograms, but this was 1.4 meters. So that mgr added up to 55. It's the mass times 9.8 times r. So that was 7. So the net torque, because they're in opposite directions rotationally, is 71 minus 55. So the net torque was 16. Get rid of this now. 71 minus 55. Okay, the I was, here it is. The I was 12. We're going to get 12. Where do we get 12, Minho?
Christian said.
It's what?
Christian said.
I should have written down more.
It says in the problem.
Oh, it gave you that in the problem. Never mind. Okay. I couldn't figure out where I got 12. I didn't read the problem. It told you that I was 12. So now, if you divide 16 by 12, you get 1.3. That's it. Yeah, it wasn't as hard as I thought. I was trying to figure out how to come up with 12, but it was in there. All right. Everybody see what to do on that? Okay. 16. We only have 5 minutes left. What do you want to do with our last 5 minutes? What's most important? What if I just read the answers to the rest of these so you know if you got them right? Number 16 is C.
All right. Nope.
Both have the same total kinetic energy. Number 17 is D, dog. Each external torque may be non-zero, but the sum must be 0. And then number 18, the ice skater, B.
Woohoo.
Okay. Now, do you want to bring up what? The 3 problems you had for homework that we did not ever go over, at least their answers are in the back. The CYU questions we never went over, their answers are in the back. I would strongly recommend you check the back and actually read those questions and see if you understand them. The same with the 3 homework problems. If you didn't get the answer in the back, you need to keep working on those or come see me. But we have a few minutes to answer at least 1 or 2. So somebody give me a question you still have. Even if it's not one of those, what question do you have now with the time we have left?
Can we do I didn't say it.
Let's do a letter one.
Well,
We don't have that
now
much
you
time
messed
to
up,
do a
right?
letter
That's
problem.
it.
Let's do a letter problem. Though. There's a lot of letters that we have to answer at the end.
Real
because I'm
quick.
not good at those.
Before we do that, why is
Okay.
16 C?
Is that a focus question?
Yes.
Okay. 16. You have the 2 rings that have the same I. It's mr squared because they have the same mass, even though they have different r. Which, well, is that really true? No, they have the same m. They don't have the same I. They have the same mass, but different r. Which hoop, if either, has the greater total kinetic energy plus rotational at the bottom? Here's the thing. Energy is conserved, so even without doing any math, the ramps were the same, so they had the same U up here, didn't they? That's just MGH. And they had the same M, right? So if they started out with the same amount of energy here, they've got to have the same amount of energy down here. Energy is conserved. Down here, it's the K plus the KR. And these may not be the same, but if you add them together, it's got to be the same. Because the total energy at the bottom has to equal the total energy at the top. That's what you know. But no, they wouldn't. These would not be the same. The one that has a greater KR would have a smaller K. But they're still going to add up to the same. Okay. All right. Okay. What else? Question?
We don't have time.
We probably don't have time for you to make up a good problem with letters.
We could do 17, a focus problem.
17.
Yeah.
Under what conditions is the angular momentum of a rotating body, such as an ice skater, conserved? When is the angular momentum of the ice skater conserved? Well, the answer was D, which says each external torque may be non-zero, but they've got to add up to 0 because the momentum must be conserved. We saw that with Sophia back there when she pulled in her arms and she sped up.
I just didn't see D because it was on the other side, and I didn't see the option.
Oh, I'm sorry. Yeah, some stupid book. Yeah. All right, anything else? We're going to turn this off. That's way too long already.
Bye, guys.
Bye, everybody.